doesn't want to show up or talk because of the recording, we can always talk via chat as well. So just remembering that. Cool. So just let's wait a bit for a minute, and then we'll start. Yep.
Sorry, my student come. So it's my turn. I can share the screen.
Yeah, sure. So everyone, welcome to our second Energy Sources webinar series brought to you by Newcastle University Centre for Energy. Thank you very much for everyone who's attending today, especially our three speakers. Today, our team is Wind Energy, and we'll be listening to very riveting talks by Professor Wood from Newcastle University, Mr. Aidan Duffy from Durham University, and Dr. Michael Smailes from Offshore Renewable Energy Catapult. They will be discussing their research project and fields, and will be available to reply any questions from the audience during our panel session that will start after all the presentations have been delivered today. And the webinar aims to promote a great discussion around wind energy and promote wonderful research and cutting edge techniques like the ones they're using in their work. So please, audience, sit back and enjoy. We're about to start, and with no further ado, let's introduce our first speaker. So our first speaker is our very own Professor Zhiqiang Wood, Head of Marine Offshore and Subsea Technology Group, and Lois Professor of Offshore Engineering at Newcastle University. Previously, Professor Wood was awarded his master and doctorate degrees in naval architecture and ocean engineering by Shanghai Jiaotong University, where he also worked as a lecturer and associate professor at the School of Naval Architecture, Ocean and Civil Engineering. Professor Wood has since then established himself as a leading researcher with international recognition in the field of offshore engineering, whose areas of expertise include offshore renewable energy, hydrodynamics and structures, and also collision and grounding of ships. With a vast and impactful record of publications, Professor Hu is also a member of the specialist committee ISSCV6, focused on ocean space utilization. Additionally, he works as a member of the Royal Institution of Naval Architects and as a deputy editor of the journal Ocean Engineering. So, Professor Wood, thank you very much for accepting our invitation to be with us today, and the stage is yours.
Okay, thank you, Anna. Can you give me the right to share the screen? I can't share my screen.
Try now.
Okay. Oh yeah. Okay. Yeah, okay. Can you see my screen? Okay. Good afternoon, everyone. The presentation title is the software in the loop combined artificial intelligence method for dynamic performance analysis of the floating offshore wind turbines. My presentation includes 4 parts, and from a brief introduction, I introduce a method called SABA, and I will give a case of study, and finally some conclusions. This presentation gives the research of my latest research on the floating wind turbines. The development of the floating offshore wind, I think, moves very quickly, and now in UK we have the first commercialized floating offshore wind farm. I think has already operated for 5 years. Very successful case. This type of the floating wind turbine uses a spar type, a supporter and floater supporter. It's a difference from the fixed bottom offshore wind farms. Besides the high wind, also called the wind floats, it's a semi-type floating wind turbine that operated in Portugal, but now has been decommissioned. And in France, a barge type floating wind turbine already been proposed. And also in Asia, as in China, they also I think deployed 2 semi-type floating wind turbine near Hong Kong. in South China Sea in last year. So the development of the floating offshore wind quickly when people want that the wind turbine to be far away from the coastline, where the water depth is larger than 50 meters, then floating type has to be used. However, to predict the dynamic performance of the floating wind turbine is a big challenge, because the floating wind turbine is a multi-body, rigid, flexible coupling system. And this, when we consider the dynamic performances of the floating wind turbine, we must consider its complicated sea environmental loads. That means the aerodynamic loads, hydrodynamic load, mooring load, and some servo load and ice, tidal, quite many types of loads must be considered. And it's a multi-body system, which means that the wind turbine is different from the traditional offshore structures. So the multi-body system will bring quite a lot of the nonlinear responses, and it is combination of rigid and flexible components, which means that the part of the structure is rigid body and part of structure is flexible body, and there are some quite a lot coupling of the interaction between the different components. So all these, I think, factors makes the dynamic performance prediction a challenging task. Nowadays, people use 3 different types of the method to calculate the dynamic performance of the floating wind turbine. The first one is the numerical method. I think that's a theoretical numerical method based on the I think the theories, fundamental theories. Here I gave an example that in my team we built an in-house program. It's called Darwin. It is built based on some theoretical analysis theories who can be used to do the analysis and prediction for the floating wind turbine. But this kind of method have some problems. For example, lack of the full-scale data for the validation, because that the wind industry is very confidential. they keep most of the data confidential, so it's quite difficult to do the validation work nowadays. So we can't say that the software calculation is 100% accurate and still needs more validation. The second method is spacing experiment method. This is very popular used in the traditional offshore engineering field. But for floating wind turbine, there comes, I think, quite many challenges. I give some examples here, but I want to emphasize first one that's difficult in considering the Reynolds number and Furrow number simultaneously in the test. So this means that if we conform to the fundamental theories, we cannot consider the aerodynamics and the hydrodynamics at the same time. So this gave a big challenge for the basic experiments academic field. So people have to find some new method to overcome this challenge. The third method probably used is a full-scale measurement method. That means that if we can use high wind in Scotland to directly collect the data, that could be much better. However, well, I say that all these data are confidential, and whether the data are reliable or not, so it's also a problem, and the cost is very high. So currently, we can have a limited amount of the full-scale measurement data, but I hope that in the future more data will be shared with academic field. So based on these 3 types of methods I introduced, then people are thinking about, can we use artificial intelligence technology? That's a promising solution. That means we combine the traditional numerical method, the basic experiments, and the AI technology with the full-scale data to provide a more promising solution to overcome those difficulties, to overcome those challenges. And we find, I think, a better solution to perform the dynamic performance prediction for floating wind turbine. Then we introduce the SADA method. So this method is a concept, it's a new concept. Its full name is Software in the Loop Combined Artificial Intelligence Method for Dynamic Response Analysis of the Floating Wind Turbines. It can be extended to some other engineering fields, but in the floating wind turbine field, I introduced some of the important contents. First is the Darwin. That means it's a foundation. This is the software. It's kind of the software that the user must know very well, and it requires that the user need to understand, to know that the fundamental theories of the floating wind turbine. So these are the first key points. The second one is that the purpose of the KDP parameters. It's a key disciplinary parameters. These parameters plays an important role between the AI technology and the traditional software. Its role is like a bridge to input those neurons from the artificial intelligence into the theoretical theories, and to help after the training, AI training, to help the software to become smarter and to become that they can become experts for the objective floating wind turbine. So this is the second key issues. And the third one is machine learning. And we can choose any of the machine learning software under the method and published every month. So there are quite many AI methods published and free to use. So, and for the first issue, let's say an in-house program. I mean that if you want to use SADA method to do the analysis, the user must have a fully understanding of the floating wind turbine and also have a software. It's not only I don't think the commercial one is proper, but the best solution is that the one that is built by the user, because they know the program very well. And for the second is that the KDP selection. I want to say more about this. This requires that the user to understand the floating wind turbine, to know how to calculate the aerodynamic load, how to calculate the hydrodynamic load, servo load, to calculate all these nodes. Then they will know that which parameters are most sensitive, most important, and most easy to be input of the neurons from the AI. So this means that the AI's role is not to replace the theoretical program, but to help or to train the theoretical program to be intelligent, to be smart. So this is the AI's role in the SADA method. The third issue is about AI itself. But indeed, I personally, I don't think it's very crucial, because the AI method published, I think, updates every day. So the user can choose the best one, the most feasible one they want to use. In my program, we choose a DDPG, this one. I think it's now it's the older one, but it published 2 years ago. So the program, the concepts can be updated every day. So this slide shows the fundamental structure of the SADA. So you can see that the Darwin program, that's the program that's in the core parts, and with the dates from basic experiments or full-scale experiments as a source for the AI training. and the right side, AI technology. The AI technology, that's the method use those data to do the training for the theoretical program and train it until finally it becomes smart and intelligent for the reference floating wind turbine. Then this method can be used to do some further analysis. And next, I want to give a short case of study. I use as high wind tolerance. So that in this offshore wind farm, that totally 5 floating wind turbine, and we get the date, receive the date from the HS4 as one of the floating wind turbine. That Equinor, that's one of the Equinor owns the supporter and mooring system. They kindly shared some of the dates with Catapult, and a few years ago we collaborated with Catapult, obtained 11 cases dates, and each of them lasts 30 minutes. So we use these dates to validate the SAD method. When we use this date, there are still some challenges. For example, that the full-scale measurement dates is not contact, meaning that there's no heat motion. Some of the motion we don't have, and we can't have the data for the wind turbine. So we have to use another one that replace 5 megawatt wind turbine published to replace that the real wind turbine. So this is also a challenge for us, that whether we can use this SADA, we can use AI to do the approximate analysis. And when in this case, we choose 108 KDPs. So this is quite important to choose these KDPs and to complete all the training and the evaluation process. I just want to use this figure, if you can see my mouse, use the figure to demonstrate the feasibility of the SAD method. The green curve is a measure date, and the blue curve is a Darwin calculation result before AI training. So this is the surge motion of the platform. So with the AI training, we can see that the Darwin program becomes smart, and its calculation results can move to the red curve. So this means that with AI training, it can help to improve the theoretical program to be smart for this high wind turbine. So this demonstrates that the utility of the SAD method. Finally, conclusions. AI technology provides a promising way to analyze and predict the dynamic responses of the floating wind turbine in a better way to do during the design stage. But the AI can, we must say that the using of the AI technology still require that the user to have a solid background of the fundamental disciplinaries of the floating wind turbine. It's not expected to rely solely on the AI technology and abandon the conventional theory and skills. So this means that we must to build a better solution based on the existence, experience, and the AI technology together. So that's all my presentation. Thank you.
Thank you very much, Professor, for your talk and for sharing your amazing work with us. Very interesting to hear about the AI and wind energy and predictions. It's very interesting. Thank you. And so now we'll be hearing from our second speaker. And remember, everyone, their panel question will be in the end of this session. So our second speaker is Mr. Aidan Duffy, final year PhD student from Durham University, from Professor Simon Hogg's group. Aidan previously obtained his master in aerospace engineering from the University of Liverpool And he's now carrying out very interesting research focused on the effects that leading-edge erosion has on the efficiency of wind turbine operation in a project that is part of the EPSRC Prosperity Partnership, a new partnership in offshore wind. Aidan's trajectory also includes a recent first author publication in Wind Energy, a major journal in the field, about the significance of bypass transition on the annual energy production of an offshore wind turbine. So, Mr. Duffy, thank you very much for participating in our webinar today. And whenever you want to start, the stage is yours.
Yep. So hopefully you can see my screen now.
Yep.
Yep.
Okay.
Brilliant. Okay, so yeah, start briefly with how I got into wind energy. So I said I did my master's at the University of Liverpool between 2013 and 2017. And towards the end of that, I started to become more aware of sort of renewable energy and the likely significance that was probably going to have in the future, not just in the UK, but kind of globally. And also my main interest at the time was really in aerodynamics. That was what I enjoyed most and what I was most interested in. So for me, the natural progression there was towards wind energy. Although the benefits of a engineering degree specifically is very adaptable. So there's pathways into kind of anything, not just within wind, but also within any sort of renewables. So electrical could go towards looking at gears and converters and generators and so on. So there's a lot of pathways, but I chose to go down the aerodynamics route. And I started my PhD here in Durham in May 2019, which is looking at the effects of leading-edge erosion on wind turbine efficiency. So sort of briefly an overview of my project and also the ties that I have there with industry because of that. So it's part of the Prosperity Partnership, which covers a whole range of different PhDs, many of which have kind of come to an end now. But that covers all aspects of wind turbine technology, from health monitoring, new blade technology, and looking at generators and converters. And there's a lot in there, and it's all connected with Siemens Gamesa Renewable Energy, who are the largest manufacturer of offshore wind turbine components, and ERSA, who are the largest operator of offshore wind farms. And so both of those I have connections with through my project, and that's really good. It allows a lot of collaboration and exchange of sort of knowledge and ideas, and make sure I stay in line with what they're expecting and what they require as industry. And the project itself works on lower or early technology readiness levels, so building concepts and proof of concept before going into later development stages to be sort of used within industry. And yeah, as I mentioned, the direct contact with the industry means to stay aligned with industry requirements. You get an output which is beneficial to the companies. Also, you gain the expertise from the knowledge of the people within the industry to improve the quality of the end product there. So briefly, a bit of growth or a bit of information about the growth of the offshore wind sector. It's one of the cheapest forms of electricity which is out there at the moment, and it's constantly getting cheaper. So over the sort of 2-3 year period between 2016 and 18, the levelized cost of electricity or energy reduced by over 50%. And because of that, there's increasing demand because of it being cheaper and more readily available. So wind turbines get bigger and there are more of them. An example of this is Hornsea 1 and 2, which are just off the Yorkshire coast, off the Humber. And between them, they cover about 850 square kilometres, which is the same sort of size as about 120,000 football pitches, for that in context. And that powers upwards of 2.5 million homes. And just one rotation of one of these turbines can power a home for a full day. So they really do produce a lot of electricity. But the problem with this sort of increased number is that each of them requires inspections and maintenance, and they have an increased cost. And without addressing those costs, that means that there's less energy to reinvest within the sector in order to help decreasing the levelized cost of electricity and also expanding offshore wind. So some of that is down to leading edge erosion, which comes about, or what I'm looking at specifically in rain erosion, is that rain droplets will impact the blade and kinetic energy builds up, or kinetic energy starts to cause damage within the blade materials and coating, and gradually that wears away and leaves a non-smooth surface. In doing that, it affects the aerodynamics of the blade and reduces the lift, and means that less power is produced by the blades as they rotate, which means also that less energy and less electricity is produced, and they become less profitable over time. Because this is a relatively new thing, wind and offshore wind, there's less understanding of some of these processes, and also to start with, less appreciation of how large an effect these things would have. So there's a drive now to have that understanding in order to improve things like repair timing and inspection timing to reduce the maintenance costs and therefore improve profitability. As I said, obviously this is something which is getting a lot of traction. So there's an International Energy Association task which was assigned specifically for leading edge erosion, or to address leading edge erosion, which was developed in 2021, so again quite recent. And that's looking at addressing some of the challenges of modelling and modelling erosion and the effects that have. And some of the things that I've done in my project are kind of directly aligned with the work packages within there. So again, what I'm doing is quite highly related to what's being designed within the industry at the moment. Okay, so before I want to go through the rest of it is sort of express the range of things that the PhD process can entail, and the range of different techniques and so on, which have been integrated and used, and the fact that it's a very diverse and open process that you can kind of get into and you can make it your own and do the things which suit you best as a researcher. So I'll go through some of the different steps I've done, and they include doing CFD, 2D CFD, or computational fluid dynamics, and annual energy production analysis methods. So they enable analysis of aerosols and assessment of lift and drag and energy, in order to view how much energy is being lost over a period of a year, for example, compared to an undamaged blade. Now, there's a model which I developed, which used to produce 3D eroded geometry, and that integrates new methods of assessing the area on the blade which is covered, and I'll return back to this later on. But generally speaking, in research, a lot of that is over predicted because there's again not much understanding of some of these processes. So try to integrate a new method there in order to make the results more representative of reality. And then the final part I've really done is experimental. So I have a wide range of things I've done. So I've done simulation stuff, coding, and experimental. And that's to get physical representation of erosion on physical models to be able to validate the CFD, and then use that to conduct wider studies for assessment of annual energy production over a wide range of wind turbine operating conditions in time. Okay, so briefly, the first of these is the CFD and annual energy production methodology. So first off, straight away, there was input from industry in this one. So that was help in developing simulation models which were in line with industry or are in line with industry standards to make them highly representative and useful on that. So I use parameters which come from rain erosion tests as inputs into the model here. A rain erosion test is a form of accelerated testing where a model is put on a whirling arm rig which rotates at high speeds in a simulated rain field and used to assess material properties which will be used on wind turbine blades in the field. So I had material from that, data from that, parameters from that, which were input into the computational model, and that was used to get things such as the lift properties up there, which is the top right graph. So I've got coefficient of lift and then the angle of attack that operates that up there. And what you can see is that as the roughness gets larger, so from this clean sort of purple line, there's a gradual decrease in the left, those properties over time become worse, which means you get less energy from the wind turbine. And then looking at something which is called bypass transition, which means that instead of naturally transitioning from a laminar to turbulent along the blade, the airflow, when there's a certain roughness, that can cause it to jump right to the location of the roughness, which is going to be at the leading edge of the blade. So in this kind of model here, it'll be right at the front. And that means, again, there's a change in the lift and drag properties, which reduce the efficiency of the blade. Then having sort of calculated those, I put into a blade element momentum model, which effectively allows you to reconstruct the blade from a series of two-dimensional sections. And then you can assess the power on the blade there, which is kind of this plot at the bottom right here. And you can see there's a gap between a clean and a rough blade, and that's the loss, which we represented in energy. Effectively, what this allows us to see is that there's a drop in the energy, and we can quantify that and compare that with what's seen in field measurements. The next part that I mentioned was this erosion model to produce a distributed 3D geometry of blade erosion. And this again started from industry input for a model to represent the damage which is caused into material by droplet impact. So it combines the droplet impact velocity and the rate of rainfall, which correlates to the size of the droplets and therefore their mass. And using material properties for the blade or blade coating, then you can work out how quickly erosion occurs, and that gives you an indication of the time it takes for material loss to start and material loss to kind of develop after it's initiated. Then in addition to this part, there's the coverage, which I mentioned, across the leading edge of erosion. And so generally speaking, that's overestimated in studies because there's a lack of understanding of how that's done, and there's not really any analyses to represent that. But that's something that I integrated here. So I've made a novel approach to predicting the area susceptible to droplet impact. And this combines the operating angles of the blade, which are dependent on the wind speed. So with wind distribution over a period of a year or longer, you can see how the operating angle will vary, and therefore the time it spends operating at certain angles. And that combined with impingement limits of droplets. And the impingement limits effectively are if the angle between the incoming droplet and the blade surface are too low, the droplet will just kind of deviate and it won't impact and impart any energy. So past a certain area or past a certain limit, there's no actual damage caused by the droplet. So these are all kind of combined, and by combining them, you get a global prediction which are what's shown in the graphs on the right here, of the area on the blade which droplets will impact, and also you can gain an idea of the percentage of time during operations that a certain area will be impacted, which will then represent the depth of erosion when applying the next part, which was using statistical distributions of roughness elements, which again came from rain erosion tests to produce a 3D distributed geometry, such as that one which is shown in the bottom left here. And the next part which was used, the inspection reports was provided by Ørsted, which again, something that's not usually available, just because of company and industry restrictions, but because of the partnership, able to get access and validate the model through that. The other part I had here, I'm trying to skip to some quickly, so I realise time is going on a little bit. Experimental tests, so basically the development of experimental models and more skills to be developed in here to have force balance testing and pressure measurements to get lift and drag values, and also infrared thermography, which allows to look at the transition location. Basically, the heat transfer rate is higher in turbulent flow, and looking at an infrared image, you're able to see the difference, such as in the bottom left here, of the colour, which shows you where the transition location is going. And this is used to validate a model with testable leading edges, which will then carry erosion, and also just to validate that it was usable and the technique was applicable to that, which is this part here. So I have an eroded leading edge, that's the picture, and did the same sort of test in the wind tunnel. Then these were applied to the CFD and the comparison made to show that, generally speaking, one is the CFD is representative of the experimental, and therefore I was able to use the CFD method in a wider range of studies to assess annual energy production losses over a larger range of operating conditions, which you've got what's shown here. So at the bottom, there's a series of graphs which shows progression over time of geometry, and at the top there's the CFD, which was used to produce the lift. These were integrated into blade element momentum model, which I mentioned earlier, to calculate AEP losses. And then you have produced something which will look similar to this graph down on the bottom right there, where there's different rain intensities, which are denoted by I, and velocities, which are denoted by V, where the higher the number, the more intense the rain intensity, or the higher the mean wind speed. And you can see there's a relation there that as the wind speed and the intensity increase, the AEP loss becomes greater. So there's more loss of energy, profitability is lower, and that's more of an effect on operators and managers. They're looking forward. So this is the kind of stage where I'm at the moment, and then the sort of future work is the last two sort of bullet points there. That each of these parameters has a specific associated damage rate, and what can be used is it can be used as a lookup or reference tool to extrapolate that to other conditions with similar damage rates without conducting further simulations, to get an idea of how the AEP will progress over time without having to spend resources on inspection and also further simulations, but you can still gain an understanding of how that energy and therefore the money lost might be, and perform a cost benefit analysis to determine when income or lost income exceeds repair costs, and therefore optimize the inspection times. So very briefly, sort of the benefits of the PSG process for me. So I've had a chance to work closely with people within industry and work towards industry requirements. I've been able to develop a range of transferable skills in a lot of areas, which open a lot of pathways into different industries and different future careers. The more visible both within industry and academia through doing things like presentations. Specifically within industry, last presentation I gave was to over 80 people within the company, including a number of managers. So the people within the company see the research overall and get more of a name to self, I suppose, and able to be seen more widely. And finally, undertake work with the potential of real world impact. So it's something which is actually going to be useful in the world and hopefully gets utilised. So thank you for listening.
Thank you very much, Mr. Duffy, for this great presentation about your work. It was lovely to hear from you. And now, everyone, it's time for our third speaker. So our third speaker is Dr. Michael Smailes, a principal research engineer who heads up the grid compliance team at the Offshore Renewable Energy Catapult. Dr. Smailes has previously obtained his master's in electrical and mechanical engineering from the University of Edinburgh and was awarded an engineering doctorate for the Universities of Edinburgh, Strathclyde and Exeter via their Industrial Doctoral Centre for Offshore Renewable Energy, the IDCOR, in 2016. Since joining our Catapult as a full-time electrical researcher in 2016, Dr. Smailes has led several impactful projects in the offshore renewables field. This included development of a patented MMC control algorithm, as well as the development of programs to automate the validation of offshore wind turbine blade, powertrain, and grid certification testing. Dr. Smailes also supervises several PhD and PDRA researches and actively participates in grid code working groups as well. So Dr. Smailes, whenever you're ready, thank you for joining us today.
Thank you. So hopefully you can see my screen now.
Yes, we can see that.
Great, thank you. So I'll just give a very, very brief introduction to ORE Catapult, who we are, for those of you that aren't familiar. For the purposes of this, our site just north of Newcastle in Blyth is probably the most relevant. We do full-scale testing of several offshore renewable energy components, most notably offshore wind turbines, including blades and nacelles and electrical ancillary components. So we do full-scale blade testing as well as full-scale nacelle testing. That includes the Haliade 150, as you can see in the picture behind this title slide, and also the Haliade X wind turbine that's going to go off at Dogger Bank in the next couple of years. So moving on, today's presentation will be on some background around electrical issues that we're facing at the moment, particularly the electrical grid, what grid code and standards are, what grid compliance is, and then a brief summary of what we've discussed. So for those of you that are maybe a little bit less familiar with electrical transmission and the requirements for that, on the right you can see a figure which is the half-hourly output or demand for electricity in the UK. As you can see, it varies significantly throughout the day, but also throughout the year. And it's a real challenge for electrical system operators to meet that demand, because they need to supply the amount of power that is demanded at all times. They can't supply more, they can't supply less, to the point of they will actually look at the TV schedule for the day ahead to try and estimate how much electricity will be used. For example, when people turn on the kettle during the break of the World Cup, they'll see enough of a spike in that for them to have to regulate how much power is coming out of the generators to to avoid instability in our grid that could, in the worst case, lead to blackouts around the UK. In order to help them do that, we have two broad categories in terms of markets. One is the power supply market. There are numerous subdivisions of this, but essentially the power supply market is, as you would expect, the market which generators bid into in order to supply bulk power to the UK grid that we use to power our homes. And the other is ancillary services market. So these are, as the name suggests again, services that generators can bid in to provide that will help maintain stability. As you're probably aware, the UK has a new ambition to build 50 gigawatts of offshore wind by 2030. To put that into perspective, over the last 20 or so years, we've managed to build 11 gigawatts of offshore wind. This is going to require dramatic change in the makeup of the generation that we have in the UK. And this will create some significant challenges for our grid operator moving forward. So a lot of the generators that they are used to, that they know, that they understand, will be taken offline in the very near future. So our grid operator, National Grid ESO, has outlined 5 key challenges that they think we will be facing over the coming years. One is frequency and low inertia. So this means normally we have a lot of gas, nuclear, and coal power stations connected to the grid historically, but these are being taken offline. These traditional sources of energy had very large generators that spun at the same frequency as the electric grid. This means that if there was a mismatch in power, then the grid frequency took time to change. However, with all of these generators coming offline now, the grid frequency will change much faster, as wind turbines don't provide that same level of inertia as standard. Stability, because of this lower inertia, the grid will become more inherently unstable. So any mismatches in power can lead to blackouts much faster. Voltage, again, the generators that we used to have consumed a lot of reactive power and helped balance the voltage on the grid. With all of these generators coming offline, this voltage balancing needs to be taken up by different sources. The fourth, thermal. The new generation plants are going to be further from population centres. Therefore, there can be larger losses through the cables and overhead lines that are not used to carrying large amounts of power will now need to carry power from far offshore centres, particularly in the north of Scotland, north of England, down to our population centres in England. At the same time, we're increasingly electrifying our demand, so more heating will be provided by electricity. Electric cars will start to replace petrol and diesel cars. All of this creates additional demand. And restoration. In case of the worst case scenario where the UK does properly black out, then we need power generators that are capable of restarting the grid. And the plants that are currently tasked with doing this are slowly being taken offline. Most notably, out of these 5 challenges, 3 of them are really ancillary service driven, and these are much harder to test and validate, particularly in a new generation. There's also a recognition that offshore wind needs to start to fulfill far more of these challenges. And so the testing for offshore wind will get increasingly challenging. So how do we currently manage this? Well, all generators need to follow grid code before they are allowed to connect to our electricity system. This is managed by National Grid ESO, and is essentially a combination of a legal and technical document, and ensures that anyone that connects to the electricity system connects at a level playing field, so no one is given an undue burden, and it ensures that our electricity system remains one of the most reliable and secure in the world. What are the consequences of non-compliance? Well, if you're a wind turbine OEM, you face the possibility that you won't be able to sell your turbines, because no wind farm operator will want to buy them. Also, the face liability issues if they're found at a later date to be non-compliant with the grid code. If you're an owner operator of an offshore wind farm, they can either be refused permission to connect or liable for any damage that is caused during blackouts because of their non-compliance. And us, the end users, well, we can see increased number of blackouts, like the one that happened a couple of years ago on the 9th of August, where we saw large parts of the UK blackout, including hospitals, transport systems, everything, which can be a real threat to life. We also have standards. So where grid codes are a legal document, standards demonstrate how generators can go about demonstrating their compliance to these legal documents. The most notable one for offshore wind is IEC 61400-21. So grid compliance testing, or what is it? It's the process that generators must go through in order to demonstrate that they have complied with the grid code. All generators all around the world always need to do this, and one of the most common standards used to test to is a standard called IEC 61400-21. In terms of the electrical standards, it's part 1. This details 17 tests that a manufacturer must do, and they might have to do this several thousand times to accommodate different wind conditions, different levels of power generation, different voltage quality considerations, etc., etc. So this is a really comprehensive number of tests that need to be performed. And this is just an excerpt from what's required. So how do generators, particularly offshore wind turbines, go about demonstrating grid compliance? Well, traditionally, what they've done is they've built prototype turbines in the field. They would need to do this in at least 2 countries to sell a turbine globally. One in a European country or a country that utilizes a 50 hertz network, and another which utilizes a 60 hertz network, such as the USA. Obviously, it takes a long time to be able to do these tests because you're relying on both the wind and the electrical conditions. If anything goes wrong, these are prototypes after all, then it can take a long time to fix the problem because they're out in the field somewhere. Also, some of the tests that need to be done, or some of the most important tests, are fault ride-through tests to make sure that the turbines can stay connected to the grid even through faults. The equipment at the moment doesn't exist for testing the largest scale wind turbines at the normal voltage, so 66,000 volts. And it's not just us saying this, National Grid has also recognized the problems. So these challenges delay turbines going out and potentially will result in turbines going out that aren't fully grid compliant. So how can we address this? We can start to bring testing in-house where we have much more control over what's going on. There are a couple of places in the world where you can do this. AEP Catapult is one of them and is one of the largest test facilities in the world where this testing can occur. Other places include Fraunhofer in Germany, Lower Clemson in the USA. So how do we do this? Well, first of all, we replace the wind with our 15 megawatt drivetrain test facility. This allows us to test full-scale wind turbines. And we replace the local grid with a grid emulator. This is essentially a set of back-to-back power converters that allows us to control the grid as the turbine sees it. Through doing this, we can create any of the grid tests that you saw on the previous slide. So we can change the frequency if necessary. We can create fault ride-through events. We can create unbalanced fault ride-through events, even overvoltage events, all while not impacting our local grid. And this is similar for other facilities around the world. In doing this, we can make sure that we can test turbines much faster, much more reliably, and more realistically than connecting out in the field. To take this even further, we can even do mechanical hardware in the loop testing. So this is where we can replace the action of the blades pitching and tilting. And we can do this by connecting to the wind turbine controller and putting the control actions through a hardware in a loop simulator, which then feeds into our mechanical drive system, so that if the pitch of the blades changes or the wind speed changes, they'll see a different torque and speed supplied by our mechanical generator, thereby ensuring that the turbine believes that it is changing the pitch angle of the blades. So quickly in summary, what have I gone through today? Essentially, the UK and indeed the global electricity system is facing significant challenges to adjust to renewable energy coming online. The grid code is an important document that ensures all generators connecting to the electricity transmission system do so on a level playing field and ensures stability of the grid. The grid compliance is the process that all generators need to go through to demonstrate adherence to the grid code. And lastly, field testing is becoming increasingly difficult, and therefore the future is moving towards in-house testing full-scale turbines. As this allows more advanced testing and more reliable, faster testing as well. Okay, thank you.
Thank you very much, Dr. Smailes, for your presentation. It was very interesting to know more about the grid code and the grid compliance as well, and the house testing. Thank you so much for your words and presentation. So everyone, in the interest of time, we're going to be moving our Q&A panel from a live format to an email format. So if you want to pop your questions in our chat or email to the email address that I just popped in the chat, we're going to send your questions to our speakers, and they're going to send either an email to you back replying, or they're going to reply on the website where we're going to put the recording of this presentation so everyone can see their answers as well. So with that, thank you so much, everyone who attended today, who came to our webinar, and to our speakers again, Professor Wood, Mr. Duffy, and Dr. Smailes as well. It was lovely to know more about wind energy and all the developments that are happening in this powerhouse field that is the offshore renewable energies as well. So thank you so much, everyone. And don't forget to, send us your questions. It will be lovely to talk to you later on. So thank you, everyone, and have a lovely Wednesday. And since this is the last one of the year, Merry Christmas as well.
Thank you all.
Thank you.
Bye.